So, you now know all about quantum field theory, so I don't need to pause and explain very much. We can just get on. There's going to be some little twist, as I mentioned, when we do the Dirac field. But apart from that, quantizing all of these fields, just applying the formalism that we have. Okay, just plug in, grind away, and then at the end we'll discuss interaction between these fields. So now, so the scalar field is the simplest one, and then the Dirac field and the covariant formulation electromagnetism just gets a bit more complicated. It's a more complicated version of the same thing. All right, but let's imagine that we're starting from the beginning, and I tell you that we have the classical, real Klein-Gordon field, and we want to quantize it. Now, I remember way back when that first lecture or two I was telling you about quantizing fields. You're thinking, what the hell, how do I do that? Now you know what to do. So the first thing you do is you find an appropriate Lagrangian density. Now, there's no magic formula for finding out what the Lagrangian is. If you can find a Lagrangian that gives you that field equation, then that's it. So we know that the Lagrangian density for the real Klein-Gordon field takes this form, and you can easily confirm that the Euler-Lagrange equation implies the Klein-Gordon equation. Okay, so you found a Lagrangian. This is the Lagrangian for the Klein-Gordon field. So what do you do? The next step is to find the canonical momentum density, phi, which comes out to be just phi dot. And so the Hamiltonian density, which is just phi dot minus the Lagrangian density, is equal to a half pi squared plus grad phi squared plus m squared phi squared. That's the Hamiltonian density, and so the Hamiltonian is just the integral over all space of the Hamiltonian density, so it's a half integral over all space pi squared plus grad phi squared plus m squared phi squared. So what have we done so far? We've just written the real Klein-Gordon field in Lagrangian and Hamiltonian form. And what we have so far is all classical. All right, so now what do you do to quantize? So the fields and the canonical momenta become operators satisfying the canonical commutation relations. Phi hat xt, pi hat x prime t equals I delta 3 x minus x primed. And instead of writing etc., let me write the others commute. The other commutation of phi with itself or pi with itself are 0. And so we have the canonical commutation relations, or seeing as pi is phi dot, we could write it as phi hat xt, phi hat dot x prime t equals I delta 3 x minus x prime, etc. Others commute. Phi dot commutes with itself, phi commutes with itself. Okay, final thing, the Hamiltonian also becomes an operator. So we have the Hamiltonian operator, which let's write that in terms of pi hat. Usually you write your Hamiltonian in terms of x's and p's. Right? You know the Lagrangian is usually, you know, the coordinate and the velocity. Hamiltonian you write in terms of the coordinate and the momentum. Here the quote coordinate is the field, and the momentum is the canonical momentum density. So we write it like this. So this is just the operator version of what I already wrote down over there. And then there's a final check, just to make sure you haven't gone wrong. Remember, we're working in the Heisenberg picture. Heisenberg picture, where the time rate of change of all operators is given by the Heisenberg equation of motion. Why are we working in the Heisenberg picture? We're working in the Heisenberg picture because the equations of motion for the field operators take the same form as the classical field equations. And that's very useful because we already know properties of the classical field equations that we can use. And so it should be that the quantum operator field satisfies the same equation. So if you apply this equation with omega equals phi hat and omega is pi hat, you can show that, let me write it like this, you can show that phi hat 2 dots minus del squared phi hat plus m squared phi hat is 0. In other words, that the operator field just satisfies the real Klein-Gordon equation that you started with. All right, fantastic. So now we can rub out all the classical theory that we started with. We've now constructed a quantum theory of the real Klein-Gordon field. We have the operator field, we have its conjugate momentum, density operator. In the end here, what is it we're really interested in? So let's rub out, so we've got the Hamiltonian, we've got the Klein-Gordon equation for the operator field, and I guess we can just work with this. There we go. Here is where we are. So this is where we are. We've got the quantum theory, the operator fields, canonical commutation relations at equal times, and the Hamiltonian. And from the Heisenberg equation of motion, which is Hamiltonian, this is the operator field. All right. Sorry, this is the wave equation for the operator field. All right, we know all about the wave equation for the operator field, so we can expand. So the solution, general solution of the Klein-Gordon equation, we can expand the operator field in plane waves. And remember, what we do is we do a finite but arbitrarily large box V. We apply periodic boundary conditions. So we have wave vectors form, volume we write as L cubed. L is arbitrarily large, n1, n2, n3 integers. So the expansion for the Klein-Gordon field looks like this, phi hat. So let's start writing, let's write x. We're going to use a bit more relativistic notation, not that it really matters, but it's just a bit shorter. So I'm going to use k dot x to mean a four-dimensional dot product. So what does that mean? It means g alpha beta k alpha x beta, which is just k0 x0 minus k dot x, or omega t. That's just the same as omega t minus k dot x. So the important bit is that k dot x is just omega t minus k dot x. So I can write the operator expansion phi hat at a point. So the point x means a point in space-time, so it's a function of time and position in space, just a slight change of notation. There we go. Here is our expansion. There's a factor in front for later convenience. We have 2v omega a hat k e to the minus I k dot x plus a hat dagger k e to the plus I k dot x, where omega is equal to the square root of m squared plus k squared. All right, as you can easily check, these plane waves. So note here, e to the minus I k dot x, this first term, e to the minus I k dot x is just equal to minus I, that is just e to the plus I k dot x minus omega t. It's just a bit short at the right, it's just the same expansion we've been doing. I'm just writing it in four-dimensional notation, okay? So, for these plane waves to satisfy the Klein-Gordon equation, the frequency has to be related to the wave vector by this formula. Okay, this can be written, this expansion can be written as phi plus phi minus. So remember the positive and negative frequency parts of the field. So phi plus has a hat only. So in other words, this first part, the sum, if I just write this sum with just the a's and no a daggers, that's the positive frequency part of the field. The negative frequency part is the rest with a hat dagger only. Just a convenient terminology, a bit useful, we'll see later. No, don't get confused between the daggers and the pluses. This is a plus, and this is a dagger. Anyway, it's just positive, it's just a notation. You can split the field into what are called positive and negative frequency parts. All right, so what have we done so far? So this is analogous to what we did for the vector potential, of course. Is there anything I've missed out? Blah, 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 blah. Okay. Okay, and of course, because we have the real Klein-Gordon field, classically it's real, the operator field is Hermitian. So this form with the A and the A dagger ensures that it's Hermitian. Good, fantastic. Now, so let's see, maybe I should rub out. We know we've got the Klein-Gordon field, the Hamiltonian we'll write down again later. Now, what do we do? So far, we have just written down the general solution of the Klein-Gordon equation where the A's and the A daggers are some unknown coefficients. They're operator valued, but they're just unknown coefficients. Now, what do? We have to apply. We have to apply the equal time or canonical commutation relations. So, let's see. All right. We have an expansion for phi. So we have an expansion for the phi dot. You can plug this in to here and obtain conditions on A and A dagger. It can be shown that the canonical commutation relations for the fields imply the following relations for the A's and the A daggers. So, A prime, etc. Etc. What does etc. mean? It means that the A's commute among themselves and the A daggers commute among themselves. Now, how do you show that? How do you show that? You show that by doing some homework. Yes, homework. So, this is a nice exercise. It is exercise or problem 3.1. Problem 3.1. Please do this. So, there are various ways in which one could derive this, but the way that they ask you to do it in problem 3.1 is that what you do is basically you take this expansion. So you've got phi hat, which is a sum over k, ak plus ak dagger, and what you do is you look at the time derivative. Let's look at the time derivative here. Now remember these terms, you've got an e to the I k dot x minus omega t and a plus omega t in the other one. You take the time derivative of this and you should find that you get something that looks like, so the first term, I'm going to take the time derivative, I'll bring down a minus I omega. There will be a minus I omega, ak, and the other term there will be a plus I omega, ak dagger. Okay, and you understand that there are factors in front and the exponential. I'm just giving you the schematic form. So you've got an expansion for phi and an expansion for phi dot in terms of A and A dagger. All right, now what you can do is you can basically think of simultaneous equations. Can I solve for A in terms of phi and phi dot? Indeed you can. So you are asked to derive the following expression. Derive the following expression. So there's what have we got? Square root 2 volume omega. There's an integral over all space, and there's an e to the I k dot x. That's the four-dimensional. Let me maybe draw a line here to separate this off. There's an e to the I k dot x, and here we have, there is I phi dot plus omega phi. Sorry, that should be phi hat dot plus omega phi hat. Okay, you can invert these two relations to find an expression for A in terms of phi and phi dot, and this is what it looks like. It's an integral over all space, and this exponential times I phi dot plus omega phi hat. Now what you can do, there are two ways to prove this. One is you might just start out by, let's just check that it's true. You could just say, I'll tell you what we'll do. Let's just take this expression, substitute in these two expansions, evaluate this integral, we should get A. How are you going to evaluate the integral? just off the top of my head, I'm guessing you're going to need to use this expression that we've written down before. Let me remind you that the integral over all space of this thing is equal to, of course, 2 pi cubed delta times the Dirac delta function, which is equal to, remember we're looking at the limit where the volume V is very large. This is just the volume V times the Kronecker delta. Okay, this is with V going to infinity. Have I written that down correctly? Yes. All right. So what will happen is, so you'll substitute in the phi and phi dots, and of course you've got a sum over all k. When you do the integral, you're going to get a Kronecker delta, and of course you'll have a Kronecker delta, which should make the sum collapse to just one term, and you should find that, okay, the whole thing reduces to AK. If you don't find that result, then you're in trouble. Come and see me, or try and figure it out. Stay up late, bang your head against the wall, stretch yourself. Okay, so you can just confirm by substitution that this expression is true, or you could look at this and you could try and be clever and say, I tell you what, let's use the orthogonality of the exponentials. Let's multiply through by one of the exponentials and integrate to bring out just one term. You can do these things, you figure it out. Okay, so once you've got this expression, so you've got an expression for A in terms of phi and phi dot, then what do? Well, then you've also, of course, got an expression for A dagger. A dagger is just the Hermitian conjugate of this. So here there will be an e to the minus I, and here there will be a minus I. These operators are Hermitian, so you have the same expression, but with I going to minus I. So you've got an expression for A, you've got an expression for A dagger. So then what you can do is you can say, all right, let's look at this commutation relation. Let's look at the commutator of A and A dagger. And I'm going to write this as, so A is an integral. Let me just write it schematically. It's an integral over, phi hat dot plus phi hat. And this is also, A hat dagger is also an integral over phi hat dot plus phi hat, but with the I replaced by minus I. And what I then have to do is work out this commutation relation. Remember, integrals are just sums. I've got a double integral I can take out. I have to work out the commutators. Phi dot phi. The only commutator that will be non-zero is the commutator of phi and phi dot. So when you take the commutator of phi dot and phi, or phi and phi dot, you'll get a delta function. Your double integral will become a single integral. The single integral, I'm guessing you're probably then going to use this again, and the sum will collapse, and you should end up with this. If you don't, you're in big trouble. Okay, so please do that exercise, a useful exercise to do, showing that the commutation relations for the field operators imply the commutation relations for the A's and the A daggers. And of course, once we've got the commutation relations for the A's and the A daggers, then we're pretty much there. We just need to, all right, so I'll leave you with that homework problem 3.1. So here we have, so we can write, so each K, we can think of a simple harmonic oscillator, and we can look at the number operator. The number operator n hat K, which is defined to be A hat dagger k. A hat k has eigenvalues. Nk is 0, 1, 2. All right, we've got the the number operator, which is just the usual harmonic oscillator commutation relations, and the interpretation. So the Hamiltonian, the total energy operator, H hat, which is given by the following expression. Instead of writing pi hat, my canonical momentum density pi is just phi dot. So I can write phi hat dot squared plus grad phi hat squared plus m squared phi hat squared equals, remember phi hat is a sum over plane waves of AK plus A hat dagger K, and phi hat dot is similarly a sum for where there's a minus omega, A hat K plus I omega, A hat dagger K. All right, just writing schematically, you know what I mean? You've got plane wave expansions for phi and phi dot, which you can substitute into here and write the Hamiltonian in terms of your A's and your A daggers, and you should get the following result, that this is a sum over K. I was going to put in an H bar, but never mind about the H bar. Omega A hat dagger A hat K dagger A hat K plus a half. Remembering, of course, omega is a function of K. Omega is the square root of m squared plus mod K squared. So you could write this with a little subscript K. If you prefer, the book does that. I don't bother. You can if you want. We did something similar to this, I think, a homework problem for the electromagnetic field. You will have derived this. So if you want, those of you who are keen, you can say, let me just check. I don't believe the books. I don't believe Dr. Valentini with his funny British accent. Let me check this. Check it if you like. But one thing I would recommend is that you check the total momentum operator. So the total momentum operator. Now you see where I have all this wonderful formalism. Just think how advanced you are now. You can tell your friends in the bar, you know you've got the Lagrangian for the Klein-Gordon field, and because it's symmetric under spatial translations, you can derive a conserved total momentum for the field, which you can then quantize, and you can write down the total momentum operator for the field, which looks like this: phi hat dot grad phi hat and again, I can substitute in my expansions. I've got expressions for phi and phi dot as a sum of plane waves with coefficients A's and A daggers. I can write the total momentum operator in terms of the A's and A daggers. So substituting in those expansions, I've got a double sum over K and a K prime. I integrate over X. I'm going to have to use this formula again. The double sum will collapse to a single sum because of the Kronecker delta. Go through it, check it all. Don't just believe me. You should get this result. Sum over K. Let me put in an H bar. There you go. I'm putting in an H bar omega and an H bar K. H bar K. H bar is 1, but never mind. A hat dagger K. A hat K plus a half. So this one here, homework. Please do this as homework. This is a sort of easier than the energy. You've got to find out. Remember, you've got to work out grad phi, of course. You're going to have to take the gradient of this expansion. So the e to the I k dot x is going to bring down an I times k. So grad, when you take the gradient of e to the I k dot x, is going to equal I k times e to the I k dot x. And just look at, you could maybe just look at the x component, work it out for the x component, and then obviously the others are going to be, just by symmetry, you should get kx here. Anyway, check that for homework. As usual, there are two reasons for doing the homework. One is to deepen your understanding of the nature of the universe, and two is that you might get a problem like this on the exam. All right. Okay, good. So once we have this, these results, then here we are. We have the physical interpretation of the quantized real Klein-Gordon field that the A hat K and A hat dagger K annihilates or creates, you can say particles, but let's say particle-like excitations, or for short, particles. Particles really is just an abbreviation. We mean these particle-like excitations of the field, with energy h bar omega and momentum h bar k. So this is, of course, just the number operator. This is the number operator, this is the number operator. So, and the number operator has eigenvalues, 0, 1, 2, 3. So the interpretation here is that, well, for each mode k, I can have 0, 1, 2, or 3, or 4, or however many excitations with this energy, which we interpret as so many particles with that energy. Similarly, there's so many particles present with this momentum. All right. And of course, finally, maybe I'll rub this out. So the state of lowest energy, so the ground state or vacuum is defined by A hat K acting on the vacuum is 0. And as we've seen before, so this is for all values of K. You could also write this as another way to define it. Some people like to write it as, so the positive frequency part of the field operator at any point in space-time acting on the vacuum is 0. It can be useful sometimes, we'll see later. Remember, the positive frequency part is the sum of the plane waves with just the A's. There are no A daggers, so each term in this sum will act on the vacuum and give you 0, so this will be 0. Anyway, the vacuum vacuum energy E0 is just from here, it is just a half sum over K H bar omega, which is actually infinite, so we've discussed this. So what we do is there's a trick where you say, let us measure all energies relative to the vacuum. Relative to the vacuum, so we're just interested in how much energy is there above this vacuum state. So what this means, so here you're going to just do something slightly different, is that in effect, so let's see, let's just write, let's take this here, P, so here we've got, this is momentum operator, this is the Hamiltonian operator. So in effect what you do, if you in effect, if you're measuring all energies relative to, so I should have said that this term here in the total momentum really comes out to be 0 because it's summing over K. Remember the K's a plus or minus, so you'll get a cancellation. Sum over K of H bar K times a half is 0 anyway, just by symmetry. So this term doesn't really contribute. But here there is a contribution, there is an infinite energy from the vacuum. And what we're in effect saying here is if you measure all energies relative to the vacuum, you're dropping this term. You're dropping this term. All right. Now there's a slightly more formal way of doing this. You can, so basically what you want to do is you want to drop the ground state term. And there's a trick for doing that. Instead of just doing this and then saying, okay, let's just forget that term, there's a little trick. Well, what you can say is you can define, well, it is just a trick. Some people think it's something fancy, but it's just a trick. Is what you can do is you can redefine all observables as what are called normal products. Now this is something that is going to come up quite a lot later. So a normal product. So in other words, we're going to replace H hat by what's called the normal product of H hat. So this is the normal product of H hat. And I'll explain what the normal product is. So very simple. So let's see. So normal product. So definition of normal product. So the normal product of any expression in a normal product all A's stand to the right of all A hat values. This is the definition of a normal product. So for example, let's say you have an expression a hat k1, a hat k2, a hat dagger k3. Let's say you have that expression appearing somewhere. And what is the normal product? The normal product of that expression is just a hat dagger k3, a hat k1, a hat k2. Or equally, so the normal product is not quite uniquely defined because the A's commute. So you could just as well flip these. This is also equal to a hat dagger k3, a hat k2, a hat k1. Or when I say it's not uniquely defined, these are equal. I just mean that the order of all the terms is not uniquely defined. The order of the A's among themselves is arbitrary. Anyway, so the normal product, the point is you have a term like this, a normal product, you just put all of the A's to the right of any A daggers. So the A's will act first and the daggers act afterwards. So something that will come up quite a lot later, especially when we do the interacting quantum field theory, is it will be useful to write down a normal product of a product of two field operators at different points in space-time. So this is, we want a normal product of, we write this in terms of the positive and negative frequency parts. Remember, the positive frequency parts contain A's, the negative frequency parts contain A daggers. So this is a normal product of, we've got 5 plus of X, 5 plus of Y, plus a normal product of 5 plus of X, 5 minus of Y. So just writing, multiplying out the two brackets. Y. And what is this? So remember the normal product. We put all annihilation operators to the right. So this contains only annihilation operators. So this is unchanged. This term here, the annihilation operators here on the left. To put them on the right, I have to swap these two terms. So this becomes 5 minus y, 5 plus x. I have to flip these around. And the rest, this doesn't change. This is already normally ordered. And here, there are only A daggers. So that can just stay as it is. So here you just, you'll see this will come up later when we do the interacting field theory. Is useful to discuss these kinds of things. Anyway, the idea of a normal product. What has been the point of this? The point of this is the claim is it helps us get rid of this term. Why? Okay, let me show you now. The trick is that let us say we've got this term here. No cheating. All right, here there's a term plus a half. But now what we're going to say is we're going to redefine observables as normal products. We're going to say, well, the true Hamiltonian operator is the normally ordered Hamiltonian. So we need to take the normal ordering of this term. And you might think, hang on, A is already on the right. What do we do? Well, let me just drop the K index. Just write A hat dagger. We've got A hat dagger A plus a half. We want the normal product. How do you take the normal product of this half? So here's what you do. Remember that the commutator of A and A dagger is 1. Okay, here we've got the same K. Okay, we're just looking at one mode K. The commutator of A and A dagger is 1, so I can write this as the normal ordering of A hat dagger, A hat plus a half of the commutator of A hat dagger. So what is this? This is, if you write out the commutator, this comes out to be a half A hat dagger plus a half A hat dagger A hat. Alright, so far all I've done is rewrite this expression as this, right, using the fact that the commutator of A dagger is 1, and then writing out the commutator, there's a minus, and A dagger A minus a half A dagger A, I get plus a half. Hang on, A dagger, plus, okay, this comes from the first term. Anyway, you can check that. I get a half A dagger plus a half A dagger A, and so the normal ordering. Now I take the normal order. I put A to the right. Here A is already to the right, so I get a half A dagger. Sorry, I get a half A dagger A plus a half A dagger A. In other words, I get A dagger A. So you see that what happens in effect, if I take the normal product of this term, the half disappears. And so, we can get rid of the half by redefining the Hamiltonian to be the normally ordered product. Now, what is all this about? Why? How do you justify this? So what happens? Basically, if I take the, because we're worried about this infinite vacuum energy. If I take the vacuum expectation value of any normal product, let's say there's any observer, I take the normal product. Remember, all the A's stand to the right. So the A's will act first on the vacuum, and remember that A annihilates the vacuum. And so I will get 0. So any expectation value in the vacuum of a normally ordered quantity is 0. So we get rid of these infinite vacuum quantities. Now, you might ask, well, how do you justify how can you justify this? Why you can't just redefine things? Well, okay, here's a way to think about this. Is what have I got this noted somewhere? Okay, here's a way to think about this. So, it's not quite as arbitrary or silly as it may look. Is that if we did classically, let us say you looked at the classical Klein-Gordon field and you wrote it in terms of a plane wave expansion, but there will be A and A star. Instead of A and A dagger, it will be A and A star. This is just a classical field. And then you worked out the Hamiltonian. You would find that the Hamiltonian, and we did this actually for the electromagnetic field, we showed that the classical Hamiltonian, or the classical total energy, comes out to be a sum that looks like this. Okay, a sum over omega A star A. Now, the point is that this, I haven't haven't quite got enough room. Let me write it classically. So here this is with phi is the sum of A plus A star. So H comes out to be a sum over K of omega A star K A K. Alright, if you do that expansion, substitute into the expression for the Hamiltonian, you should get this. But now these are classical quantities. The order is arbitrary. I could equally write this as omega AK A star K. Okay, the order doesn't matter because they're just classical C numbers. I could equally even write this as follows: a sum over K omega 1/2 A star K AK plus AK A star K. Alright, these are all the same thing. A star A plus AA star is just 2A star A, the half goes away. These are all just the same things classically. Alright? So imagine if we did the following. Imagine we said, look, I tell you what we're going to do. We're going to take the Klein-Gordon field. Instead of quantizing the operator field, what we're going to do is we're going to first write everything in terms of these coefficients A and A star. These are all just classical. I take my classical Klein-Gordon field, I expand it in plane waves, I get these coefficients A and A star, and I write my Hamiltonian in terms of A and A star. But now there's an ambiguity, of course. All of these expressions are equal. And what we can do is we can say, now let's quantize. Instead of quantizing the operator field and then deriving AA dagger as operators, we'll first do this decomposition in terms of A and A star and then quantize. But now there's what's called a factor ordering ambiguity, which comes up all over quantum mechanics, is, well, the result you get in the quantum theory will depend on which expression you choose. So here, if I do the quantize, I get an operator Hamiltonian that is a sum over K. As I said, instead of promoting the field to an operator, we're first decomposing the fields in terms of A and A star, and then promoting these quantities to operators. So I will get omega A hat dagger K, A hat K. Whereas if I chose this expression, I would get H hat equals sum over K, omega A hat K, A hat dagger K. And these are not the same, because the A and A daggers do not commute. If instead I chose this one, I would get, what would I get? I would get a sum over K, 1/2 A hat dagger K, A hat dagger K, A hat K plus A hat K, A hat dagger K. All right, and now I use the fact that A hat K, A hat dagger K, commutator is 1. And so I can rewrite this expression as the sum over K omega A hat dagger K, A hat K, sorry, this is a bit squashed here, plus 1/2. Oh dear. All right, plus 1 divided by 2. There's a plus 1/2 here. So this is sum over K omega A dagger K, A K plus 1/2. which is the original expression that we got by straightforward quantization. Okay, so plus a half. I don't know if that's any more than that. I've made it even more illegible. But anyway, you can see what I'm doing, I hope. All right, so the point is now, if we'd started with the classical theory written like this, when you quantize, you get a Hamiltonian that's a sum over A dagger A plus a half. And this plus a half is this infinite vacuum term. If instead you do the quantization this way, that's nice. If we do the quantization starting from here, then we get what we want with no factor of a half. If instead you do it this way, then you've still got this problem. Your vacuum expectation value is not 0, okay, because of this A dagger acts on the vacuum. So, in other words, if you don't want an infinite vacuum energy, this is the one you want. And so what you can say is what the normal ordering, when we say we redefine all observables as normal products, one way to interpret that is to say, okay, what you're really saying is that if we go back to the classical theory, written in terms of A's and A stars, we're going to choose the expression of this form, where the A's stand to the right of the A stars. So we're not going to choose this, and we're not going to choose this, okay, because here there's an A star on the right, here there's an A star on the right. We're going to choose this form, and then we're going to quantize, and then we get our Hamiltonian with no 0-point vacuum energy term. So that is that's the justification for the normal product. So basically it corresponds to choosing a particular order of factors before you quantize, which you can do. So let's see about the content. So let me see at this point. All right, so then what happens, so if you want to be slightly more fancy, you can say, okay, so that means that we have our energy and momentum. You can combine them into an operator 4 vector with components h hat and p hat, and this is just equal to the sum over k of h bar k alpha a hat dagger a hat summed over all k. There we go. We've got our energy, total energy momentum 4 vector operator for the real Klein-Gordon field takes this form where because we've defined observables as normal products, the 0-point term just disappears, and there we are. So let me see. Let me just do another 5 minutes, and then I'll take it if there are any questions. So, all right. So, as we saw in the electromagnetic case that we did in some detail, and there was also the polarization index. Here I can build up, let's see. So the vacuum, so we've got the vacuum. Vacuum is 0. So remember, for each value of k, we've got a simple harmonic oscillator, mathematically speaking. For each k, There's a simple harmonic oscillator, so I've got K, K prime, K double, all the possible values of the wave vector in the vacuum. All of the modes are in the ground state. In the vacuum, all of the modes are in the ground state. Now what we can do is we can look at a single particle state. Single particle state, which what do you do to construct a single particle state? You just act on the vacuum with a creation operator. This gives you a state that you can write simply like this, but beware what this means. This one here, I've got energy levels just going up all the way. For some reason I'm starting to slide downhill here. That's supposed to be a straight line, so just rotate your coordinates a little bit. It's not supposed to be sloping down. Anyway, it doesn't matter. So what do we have? K, K prime, K double prime. What is this state? It says that for the mode K, we're in the first excited state, whereas for all the other modes, we're in the ground state. And of course, so this is really a tensor product of K times, we've got the ground state for K prime times the ground state for K double prime. This is really an infinite product over, say, I've got the first excited state for this mode, ground states for all the other modes, but you don't usually, no one ever bothers to write this. It's understood. All right, so this notation, it's implicit that the other modes are in the ground state. I could also have two-particle state, where I have A hat dagger K, A hat dagger K prime, acting on the vacuum. So where one of these other states, I may as well draw it, there we go. So where I have the K mode is excited, and also the K prime mode is excited. So here's K, K prime, the other K's, and the other K's are all in the ground state. All right, so this is the a two-particle state. There are two modes that are excited. They're in the first energy state, and the way the physical, well, I was going to say physical interpretation. Let's say the physical content. Let's say, look, in such a state, the total energy is h bar omega. H bar omega plus h bar omega prime, and the total momentum is h bar k plus h bar k prime. So, this, you can think of it as, heuristically, you can think of it as the presence of two particles. There's one particle with energy h bar omega and momentum h bar k. There's a second particle with energy h bar omega prime and momentum h bar k prime. It's a two-particle state. I could also have more than one particle, more than one excitation in a mode. I could also look at a state of the form A hat dagger K squared acting on the vacuum. And we put in a 1 over root 2 for it to be normalized. So just you might want to recall the nth excited state of the harmonic oscillator. you act on the ground state n times with the creation operator, and you have to divide by the square root of n factorial for it to be normalized. So this is a state where I have here are all my different modes. Schematically, the mode K, we're in the second excited state. There are two particles with energy h bar omega and momentum h bar k. Something to note. The particles this is for the Klein-Gordon field. If the particle-like excitations corresponding to the Klein-Gordon field are bosons. They're bosons in the sense that the occupation number so n is just the eigenvalues of the number operator for the kth mode can take any value. So for a given mode, I can have, I could have 5, 10, a million excitations. I could have, in other words, a million particles in the same state with the same momentum and the same energy. There's no limit to how many particles can occupy the same state. Now remember, this is a kind of heuristic language. We're talking about, oh, I've got a million particles occupying this state. From a field theoretical point of view, you're just saying that that mode is in the millionth excited energy state. Okay, there's no, there's an infinite number of energy levels that can go up and up. From the point of view of the particle interpretation, you say, oh, I can have an unlimited number of particles in that state. So, from the, in terms of the particle interpretation, we'll say there are bosons. Something also. Well, all right. I think that's enough. That's enough about the boson. What we're going to do, what we'll see. What we'll see when we come to do the Dirac field is there's a funny twist that because all commutation relations are replaced by anti-commutation relations, it will turn out that there are no higher energy states here. For each mode, there are just two levels, and that you can have at most one particle in each mode, where each mode is labeled by the wave vector and the spin. So you can't have more than one particle with in the same state. There will be fermions. So maybe let me note here, NV. So for the Dirac field, we will find that they are fermions. All right. So what we did today, that was the quantization of the real Klein-Gordon field. You're field theorists now. Quantum field theory. We just did it. Next Tuesday, I'm going to run through the same thing for the complex Klein-Gordon field. And there we'll find that there are two kinds of field excitations that correspond to particles of positive and negative charge. They are particles and antiparticles, which when they meet, they annihilate. And all that exciting stuff. So next Tuesday, we'll do the quantized complex Klein-Gordon field. About the exam, will include material, everything that we've done up to and including today. Okay, next year the quantized complex Klein-Gordon field is not going to appear in the exam, though the classical complex Klein-Gordon field might do. You never know. But anyway, so because we've done that, you would have done that with Indra, we've done the classical complex field. So all the stuff on the field theory. Remember the Lagrangian field theory, it's more important that you know the results rather than we're not too much interested in all the finicky derivations of those conservation laws and all that. It is the tools that you need to know. So there's some tips for the exam. Please do the homework. The homeworks I mentioned today, exercise 3.1, plus deriving the expression for the momentum operator in terms of the A's and A daggers. Please do these exercises because, you know, as I've explained. And that's it. So are there any questions?
In quantum mechanics for particles, we have infinities there also.
Sorry, in the?
For particles, quantum mechanics for particles, not for fields.
Say low energy?
Yeah.
Low energy.
So we have infinities there also, the position eigenstate or the momentum eigenstate is not normalizable.
Okay.
So why is this infinity more problematic than...
Okay, well, all right, so there's a different kind. So what is happening here is that you are looking at something that you could measure the energy in a region of space. Now, maybe what you're thinking is, hang on, you're talking about the energy of the whole of space, which diverges, and maybe having infinite space is not physical. I could just consider a finite volume. But remember, I did a calculation some time ago where I showed you that the vacuum energy density is infinite. Okay, if you calculate the vacuum, so this is the total vacuum energy of the say the Klein-Gordon field. Let's divide it by the volume. We've got this normalization volume that's arbitrarily large. So this is the energy density in that volume. Okay, you find that this is still infinite. This is infinity. So the theory predicts that if I measure the energy in some finite volume, it's infinite. So you can't just wave it away saying, oh well, you can't have an infinite space. We consider a finite volume. In the case, the infinities that you're talking about, where you have a momentum eigenstate, if you have in low energy quantum mechanics, if I have a particle where we claim that we know exactly what its momentum is to infinite precision, well, the wave function would have to be spread over infinite space. Now, you can argue reasonably, well, that seems a bit unphysical. Surely in any real experiment there will be some finite volume. You can say, well, really the particle is confined to a finite volume, and so such states are not physical. You're never going to be able to define the momentum with perfect precision. There'll always be a small spread, and you'll always be dealing with a finite wave packet. Which you can argue about, which is fair enough. Whereas here, even if you say, well, no, there's just some finite volume, well, you've got an infinite energy density. So the prediction is that if I measured the energy of the vacuum, the density will be infinite, which is a problem.
When we replace a summation by an integral,
sorry?
When we replace a summation by an integral, we do assume that the volume is tending to infinity.
Well, okay, but that's just an approximation. I mean, what you can do, remember here, so the expression that we got, we took V going to infinity so we could replace the sum by an integral. But you don't have to do that. What you can do, you can keep V finite, and remember this sum, you'll get then a slightly different answer. The answer will be slightly different for finite V. But you've got an infinite sum here. The omegas you'll find the sum still divergent. It's just you'll find maybe it's a bit more tricky to evaluate what the sum is. But for large V, that sum approaches the value of that integral, which is infinite. You might think, well, maybe the sum is finite, but it's not. The sum is still infinite. You can check that if you want.
So is there a way to calculate it experimentally at the energy in a localized region of space-time?
Well, some people will say to you, you just measure the gravitational field. If I measure the gravitational field, Anyway, but it is different from what you were talking about with, you know, the non-normalizable wave function, different kind of thing. So is what I said right? Yeah, no, that's right. So the sum is still, even the discrete sum is still infinite. It's just so. In fact, it wouldn't be tricky to evaluate it. You could evaluate it to be, if you take the massless case. Take the massless case, so omega is just the modulus of k. Remember, k is 2 pi over L times with these three integers, and so you'd be summing over, well, you know, you've got these modulus, you've got these three integers. These integers are going from 0 up to infinity, so you know it's still going to diverge. So there you go. All right, any other questions?
How do you differentiate between two particles with momentum k and one particle with 2k?
Right. So let me think. So all right. So they have the same energy. So the total energy is the same, the total momentum is the same. So what would happen? I mean, in a real experiment, if you detected the particles in the case where there's one particle, what you would do, you would get one detector here would click. I've detected, oh, there's a particle with a certain momentum 2k. Whereas in the other experiment, I could have two detectors that click, where each detector has detected a particle with I mean, it's not obvious from this, but the way it works in terms of when you actually detect the particles, in the first case, if I had, say, a lot of detectors where each detector could be triggered by one particle, in the first case, only one detector would fire. In the second case, two detectors could fire.
How do you resolve that here?
So what you really need to do because realistically there's a slightly unphysical thing here which is related to what Indrajit was saying about non-normalizable states. We've taken a single particle state to be a state of definite momentum. Realistically, a single particle state is a finite packet which is a superposition, there's a certain spread in momentum. And so if I consider a single particle state, this is a superposition of different momenta. It can be, you know, peaked around a given momentum value, but let's say there's a small spread in momentum. And so the particle packet has a certain localization in space. So then I can think about, well, you know, it's not an infinite plane wave. The particle packet has a certain localization, and it can hit a detector here. Whereas if I have a two-particle state, I will have superpositions. I have a spread in k and a spread in k prime. So that means I can have, you know, one particle packet is concentrated around here, one particle packet is concentrated around here. This one can hit this detector, this one can hit that detector, that kind of thing. So in a way, you know, I mean, you're right what you're saying. If I look at the strictly plane waves, I've got states of exact momentum. It looks a bit odd. Hang on, how can there be any physical difference between these two things? But actually, realistically, if you look at superpositions of momenta, so you build up packets that have some spatial localization, then you see that there is a difference. So I hope that's...
So is there a problem with the formalism?
No. I think that there's no problem with that. I mean, you could build up what you would think of as a position space wave function just by superposing different momenta. So, and if you superpose these different k's and k primes, you would have a wave function, a two-particle wave function in position space. So, so there you go. Okay, so next Tuesday we're going to do the complex Klein-Gordon field. Please do the homeworks over the weekend, And remember, next Thursday there is the exam. The exam, 8 a.m. sharp in this room.